Another linearizing question. This one's quite similar to the one before. It's just that rather than give us a graph, they've actually given us the raw data. So part A, again, we're told that the data followed a polynomial this time because x is the base number rather than the power. And again, they're just asking us to show how we could linearize that. So if we start with the model, take logs of both sides, and again, yeah, we've gone for log to the base 10. Okay, so same two steps as for question 4. We're going to separate out the right-hand side into two separate logs, and then we are going to bring that b down as a coefficient. Then we'll just do a final check that we have got exactly what we were supposed to get. So yep, I think we're fine. We've got log to the base 10 of y is log to the base 10 of a plus b times log to the base 10 of x. So we're good. Okay, so for part B, we're asked to find b to two significant figures. So looking back, so we've got this linear equation. So if we compare that to the general equation of a straight line, oh sorry, no. Log to the base 10 of x is my variable, so my gradient is just b. So basically I want to find the gradient of this line here. So I'm not going to bother drawing the graph out. I'm just going to do change in y over change in x, except it's not change in y over change in x, it's change in log to the base 10y over change in log to the base 10x, because they're the two variables that are actually plotted on the linear equation. So let's just do another table of values. So we want log to the base 10x against log to the base 10y. And actually, I may just work out the first and last values, because if I'm trying to find the gradient, I want the two extremer points as I can get. So rather than do every single value, on the handwritten solutions we have a table with all the values in. Okay, but just to save time here, I'm just going to do the two most extreme values I have. So let's do log to the base 10 of 0.5 is minus 0.301. Let's do log to the base 10 of 1.4. So 0.416. And then let's just go to the other end of values. So log to the base 10 of 8. And log to the base 10 of 5.7. Okay, so if you look on the handwritten solutions, we have got the whole table of values, but actually to calculate the gradient, I will just do the two furthermost values. So the gradient is going to be the change in log to the base 10 of y, because that's my y coordinate, over the change in log to the base 10 of x, so 0.903 minus 0.301. So let's just quickly type that in. So 0.759. I mean, I could even have typed this in actually just using the log. So just typed in log to the base 10 of whatever that was, log to the base 10 of 5.7 minus log to the base 10 of 1.4, and then I wouldn't lose any accuracy at all. But as long as I only need my answer to two significant figures. So it's minus 0.301. Okay, so that's coming out as very close to a half, but I think if we just double check, yep, it wanted the answer to two significant figures, so I'm going to give it a 0.51. Okay, and then the final part of this question just asked me to then use my equation to find some values. So I do have the linearized equation, but it's going to be much easier to go back and use the polynomial model. So they've told me what A is for this one. So A is 2.0. So they want to know what Y should be when X is 6. If I use this rather than the linearized version, I don't have to work with logs at all at this stage. It is literally just subbing those values in. 2 times 6 to the power. And if they've told me to round to two significant figures, then that's what I'll use in my working. And then doesn't, oh yeah, no, and again it does say here two significant figures, so that's going to be 5.0.